about Wallach. He is professor in the Department of Material Science and Engineering and Metallurgy, in the University of Cambridge. He's told us about some topics very interesting and very exciting about sustainable development, how materials science is providing technological solutions. His expertise is very wide, so that I'm not going to say anything about this.
Good enough.
And I know that you are waiting for him, and I stop here. And thank you very much, Rob.
Thank you.
Welcome.
Thank you very much.
The time is yours.
Well, I would like to start by wishing you all a very good afternoon. Because I was so late today, I do apologize to you all. It was a bad morning. So what I want to do is, many of you I've been able to share last week and really enjoyed, and so thank you for that. But what I want to do now is to, for those of you who were with me last week, of course, to continue the story, and for those who weren't, now you know what you will have been missing, maybe. So when I was with you last week, it was all about sustainability. And as you know, the problems with sustainability is we talk often of the technical side, but if we do not get the social and the economic all together, we can't have sustainability. And sustainability is only possible if all of these are together. Now, I'm not going to talk very much about the other issues of social and economic, but clearly they are really important, as we know, for many different reasons. But what I want to do is to look more at the technical side relatively quickly. And never forget this definition. It is a very good definition because it allows us to do what we want, but without affecting the future. And for those of you who were here last week, there are one or two slides which are the same, but not so many. Now, in the year 2000, the United Nations said they wanted to do different things, and they now are only another 7 years before they have to achieve all of these. And as I said to you, there's one missing, of course, which is the technical. But a lot of these other ones, material science can help with. And we'll look at the business of health, for instance, the business of food, as we go through. And technical, clearly, is the focus for this morning. And clearly, they are relevant to sustainability. And I should say one thing now at this point. Now you know how I talk. If you do not understand it, please interrupt. If you have questions, please interrupt too. It's important. Now, these are the issues, and again, material science is a very exciting subject, a very exciting discipline, because we can help with really all of these. We'll see at the end why I have not touched on this, but we will come to that one at the end. And what I want to do is first start about the Earth's resources. And again, you will have seen this. We know that many years ago, we used materials, so the rate of using the use of materials is here, how much we consume, and this is time. And 300 years ago, as we used something, we would finish with it, and we would put it back in the environment, and it was continually recharging, replacing itself. But nowadays, we are starting to use at a higher rate, and if we consider the rate, it is the gradient, and if we continue for the next 23 years, we will use the same amount of material as we used over 300. And that is a very frightening idea. And of course, it is quite explainable because we know exactly why this will be, because there is the population. And it matches what we expect in terms of the population. So we have a challenge. Because material science has a challenge. As we use things, if we went on this rate, then as things start to happen, they become very scarce. They do not continue. We run out of materials, and they become expensive. So what can we do? Well, if we just take some of the materials, this is how much there is on the Earth and in the Earth, and this is the amount we produce each year. And when we are up here, we don't have to worry because this is so much material. It is a logarithmic scale, and we're saying there's over 1 million tons of material, and we're not using it at such a rate, so we have a large number of years to be able to continue to use it. But if we look at one or two materials, I'll just take one, indium, the touch screens on our phones, the tin indium oxide makes the touch screens possible. There are two types of technology, the old type resistance, the new type capacitance. And as a material scientist now, immediately we have to find a technological solution. So what can we do? And these are the screens for the future. Graphene, that wonderful carbon on the two-dimensional, which has got many interests, and in Britain, we are starting to spend a lot of money to try to find applications. In Spain, the same? A little bit, okay, because it is a very exciting new material. And this, again, is where material science can immediately happen. But what is the real big development is the same way that we print newspapers, we can start to print electronic devices. And by putting layers, we can make, effectively, solar cells by putting rolling metal, or rolling, in this case, inorganic materials, to make new semiconductors, and therefore to make new solar devices. And this is another possibility, just using silver. And if we go back to the earlier graph, we will not run out of silver, not for a long time. And before we run out of silver, those of you wearing earrings can melt them down and donate the silver, unlike the indium oxide, where perhaps there is not the possibility. But silver is interesting. This is making very narrow wires, and so it is like a graph paper, like a grid. And because effectively it's much cheaper and more conductive, then it's actually going to make a big difference in terms of the cost of our screens. But more excitingly, we have the possibility of doing this in a flexible way. So now we can start to print onto flexible substrates, polymers, and that means our solar cells are no longer on single crystal silicon and brittle, no longer on amorphous silicon. This actually has some intrinsic layer between the P and the N junction, so it's based on the same idea as amorphous silicon and polycrystalline silicon. But the beauty is that it is now flexible. And that offers many, many possibilities, not just for solar cells, but as we want to read and we have paper, we can start to do it in this way. And so we're going away from the indium tin oxide, already material science giving one of its solutions. Now, how else can we help with the Earth's resources? These are our materials, and it is like a menu when you go out at midnight in Madrid to have your meal, a bit later than in England, but when you go out and have your meal, you can choose, and we have the same. And it is a menu like, again, in many good tapas bars, where increasingly there are more choices. So there are always new things to try. Now, just to remind you, if we take a material, it is in the earth, and we have to dig it up. And so we have the natural resource, and then we have to we move it somewhere, we have to put in chemicals, and we have to put in the material itself. And that is how we can make aluminium, steel, titanium. And we have residue, we have waste. And the waste may be emissions, CO2, it may be particles, and it may be something which is not good for us, toxic. And at the same time, these are the things we drive around. Now, in each stage of an object, what we're going to find is we take the material, we make it into something. We make it into maybe the cameras, we make it into a car, we make it into a bicycle, into clothes. And that, again, requires the same ingredients, the same things to put in. And it also has sometimes the same or different emissions, things we do not want. Then we use it, and then we throw it away. And when we throw it away, maybe we don't have to throw it away. Maybe what we can do is we can actually recycle it in one of two ways. So it's becoming an increasing circle. Why do I say this? Because again, we have to think about the effect on the environment. And we have to think about eco-indicators, and we have to think about what they're going to do. And there are two big eco-indicators. The two big ones are how much energy do we put in, because energy is increasingly more expensive, increasingly a problem if we're not careful with greenhouse gas emission. So we want to reduce the energy, and of course we want to reduce all of the greenhouse gases, not just CO2. And so we can find ways of doing this, and what we can do is we can say, let's look at the energy, in this case only, against those stages. This is the making of the material, this is making the object, then it is moving it to where it is. This is increasingly important, which I didn't have on the previous one, but increasingly important. If we make things near where we live, we don't use energy when we transport it to where we use it, and then we use it. So if I take an aeroplane, nearly all of the energy is in its lifetime when it is flying, not so much energy in making the materials or making the aircraft. But if I take something quite different, if I take where we park our cars, then making the cement is very energy intensive, and it also gives out CO2. But in using it, we just pour the concrete, mix the cement, make concrete, we pour it into place, and then it sits there. No energy is needed. So we, as material scientists, now can say, in the aircraft, how can we make our aircraft lighter and more efficient? And of course, we go to fiber reinforced, as in the new Boeing aircraft, which in 2 weeks maybe will fly again. But it did not fly, not because of the problems of the material science there, it was the fuel cells. But if we want to make the plane better, we have to make it lighter so we use less fuel. If we want to improve a concrete car park, we have to find different ways of using less energy in making our cement, making our concrete. So we know where to target. And just like on the phones, we know that it is the tin indium oxide, which is a very important part to replace. And it also, if we can actually replace it in the ways I said, maybe we could have phones which we can fold, because we could have them on a flexible screen. So when we're tired of listening, we roll it up and put it in our pocket. In other words, it doesn't have to be on the glass or the more rigid substrate as it is. So material science, in selecting materials, we have a tool to do this. And similarly, we can do it on emissions or any other barometer that we wish to look at. Now, design. This is a wonderful British story. Britain is really good at doing things and then getting it wrong, sadly. And this, if you look carefully, is one of the original it is the first commercial jet aeroplane. And if you look carefully, you can see just about the windows here are not as we know windows in aircraft nowadays. They were square. Very sadly, in 1954, so now over 60 years ago, in 1954, or just about 60 years, they flew this, and 2 flights with people on it just disappeared. So they decided not to fly anymore. And after an investigation, and remember, they didn't have the tools that we have nowadays, so they took a big swimming pool, and they took part of the fuselage here, and they pumped it full of water, backwards and forwards, backwards and forwards. And what, as you all material scientists will know, is, of course, at the square corners, if we pull something, we find the stress, the load over the area, the stress is much greater. So the plane has a high stress at the square corners, it is vibrating, and of course, that is a consequence for growing a crack, and it is by fatigue where we have something which is vibrating. So it was fine when it first started, but after a number of flights, cracks would develop in the square corners, and they would grow, and at the high altitude, the high pressure inside the plane blew it apart. So we learned a lot about fatigue. Or rather, we didn't, even that was before my time. But people learned a lot about fatigue. And of course, we are material scientists, we learn very quickly. Or do we? Because when you take something, this is again a finite element model, if you pull this is just half, it has a round hole. And when you pull it, you see the stress is about 3 times here than it is on the area here. So a round hole, it looks innocent, it looks simple, but even here, the stress is 3 times as great. And some 30 years later, this is the new way of flying. If you have a sports car, you often take off the roof when you drive. Now, if you go on an airplane, you can take off the roof when you fly. Unfortunately not. This happened in Hawaii. And when you look at an aircraft, you see the small holes and rivets where the skin is held onto the wing and the body too. And the stress on one of those, again, a fatigue crack grew. And luckily, luckily everybody is still staying in with their seatbelts. One person was killed because sadly, she was a flight attendant and of course was walking around at the time. But do keep your belts on when you're flying. There's a good reason now. Okay, new materials. If I was in England, I would have a demonstration here. When you take an amorphous material, our normal crystal structures look something like this. And so we have this is hexagonal, clearly. We can have cubic and different forms which you know. If we take an amorphous material, then what we're going to find is a quite different structure. In other words, there's no long-range order. There's short-range order. Around each atom, you will find others clustering. But as you go further away, the order has broken down. When you drop a ball onto this, it will very quickly absorb energy because the whole structure can move backwards and forwards, taking energy in an elastic manner. When you drop a ball on here, it's much less able to take in all of the energy on the first time the ball hits it, and so it will bounce many, many times. And there's a very elegant, have you seen the demonstration of this with an amorphous? Okay, well, next time I come, I'll put it in my luggage because it's very dramatic. And if you are a keen golfer, and I believe there are 1 or 2 of you who are keen golfers, you would want your golf club to be made from this because it takes little energy when the ball hits it, and so the ball will travel a great distance. But amorphous materials are now, amorphous metals are increasingly used. And this is an example, again, in our mobile phones. This is when you apply a magnetic field, you induce in your material a magnetic field. If it is something which is ferromagnetic, you can get a permanent magnet, so you have taken off the applied field and you have a residual magnetic field. You reverse it, and you can go around this repeatedly. And this is what is done in dynamos and transformers as your magnetic field is changing direction as your motor or dynamo rotates. The problem of this is that whilst you can get a good magnetic field, you are losing energy every time you go from one magnetic state to the opposite. The interesting thing of the amorphous materials is their hysteresis loop, the amount of energy they lose, is very, very much less. And so not only do they have interesting mechanical properties, but they have very interesting magnetic properties. And so again, they are widely used, and we will see more. What about learning? Where do we learn from? We don't really learn. We learn from each other, of course, but what we really do is we copy. We copy always. And what we do is, if some of our fellow colleagues are smart, they look at the natural materials, and they say, why is this seashell so strong but also so tough? Why does it absorb a lot of energy when I try to break it? Have you tried to break a seashell? Who has not tried to break a seashell? Okay, well, you have to come and do the experiment. It's important. When you break a seashell, is it easy to break it? Well, some saying yes and some saying no. And that's interesting because, again, this reflects the difference in seashells. But many times it is very difficult to break a shell. And the reason is because this is a section through the shell, and it is like a layer. So the crack has to grow and propagate, not in a straight path, but absorbing energy with a much longer path. So if we want to design composites, we can do exactly the same. And that is the basis of modern composites. Now, the important thing, well, the modern composite, although people say, let us put our fibers into our matrix, it's actually very important not to have the fibers perfectly bonded, really, really strongly bonded to the matrix, because sometimes you want to design it so that when it is breaking, then the fiber will pull out of the matrix, and in pulling out, it absorbs a lot of energy. So it is both strength and toughness, the absorbing of energy. And this is what the seashells are good. We have similar things in bone and in wood. And in wood, for instance, we have the most interesting structure. Have you studied much on wood? A little bit? Okay. Luckily today we haven't time, but we know it is made up of many different helixes, windings. The cellulose molecules maybe wind at this angle here, at this angle here, and they therefore give, like a composite, many different layers, and because they are at different windings, enormous strength. So another question, who has tried to take the branch of a tree and pull it in this direction and broken it? Anybody succeed? Have you succeeded? Oh, you're very strong. But it's very easy in bending it to break it. And it's because, of course, this has to be hollow too, because from the roots up to the tree top, to the leaves, we have to transport water and the food, the nutrients for the tree. And so it is hollow. And it's like a drinking straw. When you come to break a drinking straw, you cannot pull it, but if you bend it this way, then you set up a local Euler buckling. Heard of Euler buckling? Maybe, should have. And so again, it is the collapse of the wall. And we use this in many different sports activities. And my favorite two here, well, actually, I like them all. No, I'm happy with all of those. But in many sports nowadays, we use different fiber reinforced materials. And this, again, is at the weekend. There was Formula One racing. And did anybody crash? Anybody watch it? Oh, just checking. I didn't watch it. But when they do crash, you can see this here. Now, this, at first, you may say, oh, that is smoke. And maybe there is some smoke from the tires when they grip. But that is not just smoke. These things now are made out of carbon fiber in a matrix, a polymer epoxy matrix. And when they crash, they're going so fast, there's a lot of energy. And what they need to do is to absorb the energy. So again, material science can give the solution, because rather than bond those fibers so tightly to the matrix, the fibers are bonded strong enough to give the strength. But when it hits, they can pull out. And what you're seeing here is lots of fibers, because in pulling out, they're absorbing the energy, And then we all know what happens. Maybe they're not so friendly to each other, but at least they do walk away and can argue about it. And so the ability to absorb energy is very important while also having strength. And that, of course, is where we use them for the very big wind turbines now, where there's very, very big blades, because again, the stress at the root, the stress at this region here, we have a very long, these are small, but the modern ones are maybe 65, up to 65 meters, just one blade. That's a very, very big distance. And that is the biggest that Siemens is now making. Now, again, we need the lightweight, we make them hollow, and hence we can have these big wind turbines. And as you can see here, that was supposed to be 20% by 2010. I left that in because I think it didn't quite make it. The economic situation has sadly affected that. But Spain, I think, is doing a lot on renewable energy. And of course, I mentioned the 787, the Dreamliner, which has been very successful. It hasn't flown for very long. Its first flight was less than 2 years ago. And of course, we also know that just after Christmas, it could not fly, but that was not due to the structure. That was due to the fuel cells. And again, that's another area for material science, as we will see. And finally, recycling. Do you have the same number of garbage cans, waste bins at home? Oh, well, not me. We have 3 now. I hope we don't have to have 6. In Switzerland, probably they are now up to 15. Who knows? But each country. But why this is interesting is because when we fill our dustbins like this, yes, we sort it into our different. But there's real science and technology. And in London, they have just opened a new recycling plant. And this, again, is very high technology. There are video cameras, and the video cameras can distinguish easily 8 colors. And they do it at a very high speed. So they can take at 3 meters a second, and they can sort in an hour around 2,500 kilograms. This is a lot of waste. And it means we can start to reprocess our materials by collecting it. For polymers, we have a problem, because they all look much the same. But infrared spectroscopy, again, you can adapt, and you can now get 4,000 kilograms per hour to distinguish the major type of different polymer. And this has been a big breakthrough, because otherwise, if you're making polyethylene and you have a polyvinyl chloride PVC bottle in it, it can ruin the whole of the polyethylene recycling. And so making sure we separate correctly is very, very important. Notice still only 12 different types of polymer. That's not enough, but it's a big step forward, because when we make things and use them at home, we're generally using maybe only about 5 or 6, the majority of polymers. For polymers too, we can sort using atomic emission spectroscopy. So I've just put this in to say again, not maybe truly material science, but material science, the need to separate these materials is clearly material science. The technology exists. And I don't know, again, this is something that when I was much younger, we used to talk about the food at breakfast, the cereal. And it used to be said the cereals are not very good. They're very sweet and they're not very good for us. And people used to say if you eat the cardboard packet, you get more food than if you eat the cereal itself. I don't know if that's true. But what we have here, these are Marks & Spencer's is a bit like Cordon Inglese, and it sells good foods, and these are chocolates. The chocolates are very delicious. When you come to England, please tell me, and I will invite you for chocolates at Marks & Spencer's. But now they're putting them in biodegradable plastic trays. And this is cornstarch, and it therefore will break down in water. In England, we have not really moved to biodegradable polymers. And the reason we haven't is the cost. They are too expensive, and also they take a while still to break down. So biodegradable polymers, again, is something, there's an area of technology if we're going to go on using polymers the way we do. And you all will have seen pictures of the Pacific Ocean where there are these big new islands almost of polymers, waste polymer. It's really dangerous, and it's not good. And there's a different one. These are plastic bags. This is showing a big, large number of waste plastic bags which are no longer used. And again, this is good because you can actually take CO2, go to polypropylene carbonate, and blend it with starch. So it has 2 things. It's biodegradable, but we're also starting to remove CO2. But maybe a lot more work needs to be done. If we can find a way of breaking the polymer down fast, it would be really good. Not so fast that when you're going home with your shopping and it's raining, that you do not end up with your plastic bag in one piece, but faster than the time it takes at the moment. Poverty and social inequality, not for today. It's another story. But I showed you this last week, those of you who were there, and we have the problem, maybe it's only 4,000 litres of water, but that's a lot of water to produce a meal like that. And anyway, in Spain, you shouldn't be doing this. You have wonderful food. Please don't do this. You don't need to. But we have the contrast. And again, I'm not going to go into the detail. This is a major, major issue. It's a major issue in the amount of water. It's a major issue, too, in people suffering unnecessarily. I say unnecessarily because we already have the technology. These are the pipelines going across Europe for natural gas and for oil. And to put a scale on this, you can see this is about 1,600 kilometers, and that's not even the full distance. So we have technology to move things when we want to. Britain is not even as long, just about as long as this. We cannot transport water from one end to the other. Sometimes we do not have enough water in the south. In the north, in the west, they always have water. We don't do it. Why don't we do it? Because of the economics of it. And we could do a lot for people who don't have any water at all, simply by having solar power or wave power, water power, to provide the electricity and then to run desalination plants. And I'll mention desalination later, very briefly. And in fact, there's an experiment now in Australia where in the desert, they are just doing that. But they're doing it to grow crops. They are now making very large greenhouses, and it is powered by the solar and by wave, and it is basically growing vegetables in a very hot part, providing the water from desalination. So we can do it. The technology is there. We need to do more on water, but we'll see. So what about hip implants? Well, again, anybody here have one of these in them? Oh, you might. But they don't do it on young people for two reasons, because hopefully our bodies are still healthy enough and the wear on the joint is not so much we need it replacing. If this person goes through airport security, he or she always has a problem because of the metal. But it is very simple. It is either stainless steel or titanium alloys, mainly now. And this is a polyethylene cup, and that sits in the hip joint, and then the metal goes into your femur. And it's glued together by something which is almost like polymethyl methacrylate, perspex. Familiar with perspex? Polymethyl methacrylate, you can see it's the polymer you can see through. So it's not the technology is very easy. But there is a problem. And there's a lot of work now going on replacement hips, on knees, on elbows, many, many different parts. But on the hip, there's a particular problem. Well, on all of them. The metal is very stiff. And so when you're walking on it, it is the metal that takes most of your load. Bone, our natural bone, needs exercise. We all need exercise, but bone itself needs to be strained a bit, just a little bit, milli-strained, very little amounts, to stay healthy. And this is why people in hospital are given exercises, people in space have to do exercises. All of us should do exercise. Now, what we have, therefore, is the metal taking the load. The bone is now shielded here. It's in contact, and it's not being strained enough. And the consequence is that this will loosen from the bone. So you're walking along, and your leg falls off. All right, maybe it doesn't fall off, but obviously it would give you a lot of pain, and it would not be working. So there are various things you can do about this. And one of the more silly things is, which some people in Cambridge did develop, they try to match the stiffness from this region to the bone, which is much less stiff. And they did it by having a layer of needles of stainless steel. And it was a mixture of stainless steel, which is austenite, non-magnetic, and ferritic, which is magnetic. And they put this in place, and then by using a magnetic field, they could move some of these so that you started to get a variable modulus, a variable stiffness from here to there. I'm not sure about that technology. What I would prefer is this one, and this again is some colleagues in the department do. This is hydroxyapatite, so you can see the elements, calcium, oxygen, hydrogen, and phosphorus, very natural. And this is artificial bone. And so what this is quite porous. It is like a ceramic. Because it's like a ceramic, unfortunately, it is brittle. So you could not make the metal part that goes into the leg out of it, because if you were very enthusiastic and jumped up and down too much, maybe it would break. But what you can do is you can make very small bones. And a colleague went to London where a surgeon was replacing, in a child who could not hear, one of the very small bones in the ear. And it's not a load bearing, so it doesn't need mechanical strength. And Ruth said when she was there and when the child woke up from the operation and the first time could hear in his or her life, I don't remember, in his or her life, it was the most exciting moment. So even material scientists, you can see the result of your work in a very good way. But the hydroxyapatite is a really interesting material. My guess is that we will start to be able to make composite materials with it, in which case, again, we could have strength and toughness, just as we do in the Boeing aircraft, and also the European aerospace programs too. And the good thing about hydroxyapatite is that it can grow into the bone, so it becomes totally compatible. So again, biomaterials, a very exciting area. Now, many of you may have already had your heroin this morning when you woke up. How many of you had heroin this morning when you woke up? Oh, well, just checking. And when you have your heroin, when you have some drug, we know that when you first put it in, we have a high concentration. And then as time goes on, the concentration decays. If you take a pill, maybe it dissolves and then it starts to give out the benefits of why you're taking the medicine. If you look at modern pills, they are shiny and they have a polymer coating sometimes on them. Now, the polymer coating is not just to help us to swallow it, but it is also to aid the delivery of the drug. Because the diffusion through a metal is x squared proportional to t. It is a parabolic relationship. But through a polymer, you can have a linear diffusion. It is the way that the fluid interacts with the polymer. It is an interface reaction. It occurs where the fluid meets the polymer. And the rate that moves in is linear. It is constant with time. And so what you can do is you can now have, you take your pill, yes, you have to get a bit of the body fluid to react with the polymer, and then the reaction becomes linear with time. So you get a constant amount of drug with time as opposed to a very large amount and then it drops off. And this is, again, a real help. It's just a simple polymer. So health again. And finally, we know about metal structures. I mentioned them earlier. We know, again, from martensitic transformations, transformations which are not dependent on diffusion, the movement of atoms, but which are dependent on a lattice structure suddenly changing shape, normally because we drop the temperature. So we take this structure, and as we drop the temperature, all the atoms, ions, stay in the same neighbors, but it changes its type of structure, and it looks, therefore, slightly different. When we pull this, we can straighten this out, and then when we heat it again, it goes back to this structure. So notice it's this shape. Now we pull it, change its shape, but by heating it, it goes back to its structure, and then by cooling it, it comes back to the same shape. Now, this is a useful material, and again, I would have demonstrated it normally, because what we're now able to do is these materials are very easy to be able to use in medical devices. And this one is done by heat, but you can also do it by strain. If you have an artery which is not wide enough, then you have to go into hospital, and they put something called a stent. It is this shape, it looks a bit like chicken wire, and they put it in the artery to hold it open. The old way of doing it is very intensive. It's a big operation. Nowadays, if you can use the super plastic material, so the example I was just showing, you can make this very small. You can slide it into position, and then you can blow it up when it is in position. So you can do it with like needle surgery. So you have something very small, and only when it is in the vein do you open it up. So like the super plastic, this is super elastic, but it does the same. And again, this is really helpful. And if any of you have relatives who need a stent because their artery or vein is collapsing, it's a good way forward. So material science providing through the crystallography a way forward. And I mentioned water. Again, polymer membranes are increasingly interesting. There are options now of making polymers to clean water. So one way is to filter using a membrane fiber, and there are many approaches in this sort of way. GE are a major developer of this, and they're very, very small holes. So we're now talking about 10 nanometers. The problem there is keeping them clean. But again, it's polymer science coming to the solution. But another way of doing it is lighting. Are you all familiar with LED lights? Okay. LED lights, we know why they're so good, because the normal light bulb, the halogen type of bulb, maybe its lifetime is 5,000 hours. An LED, the lifetime can go up to 40 to 100,000 hours, 20 times more. And it's much lower current, much lower voltage that is needed to drive it. And therefore, the power is much, much less. So you have an advantage that you only have to change it maybe 1/20th of the normal light bulb, and therefore you're saving enormous amounts of energy and gaseous emissions in making something. And also you have much less power being used in its life. But there is another use for LEDs. LEDs can kill organisms. They can kill microorganisms, things that are in the water. In other words, their DNA is changed. Now, it is high-energy UV light that will do this. And the short wavelength is generally blocked by the Earth's atmosphere. So the bacteria, the microorganisms, are resistant because there's no sunlight. Sunlight, if it had the high enough energy, would kill it. But it's not being that sunlight is not coming into the Earth because of the short wavelength. So what you can do is you can use LEDs to purify your water. And so effectively, I have a colleague who is now developing LEDs for lighting, but a spin-off, an extra benefit, is to use the LEDs to purify water. And it's very fast. So if you have enough of the LEDs, you can clean water very, very quickly at high rates. And so again, is it new though? I mentioned about learning from nature. Over 100 years ago, in 1903, the Nobel Prize for Medicine was given because Niels Finsen realized ultraviolet light could help with tuberculosis. So don't forget to read your history, because we can learn a lot from history. And don't forget to break your seashells, because we can learn a lot from nature. So LEDs. And I showed you this. I just put it in again, just because in case some people were not here last week. We know that being overweight is not a good thing. But I want to also always remember it's always important to think from the other way around. Because if this person became thin and everybody became thin, they would release 20 billion tons of CO2 to the atmosphere. So maybe fat people are doing us a good service by keeping some CO2. So now pollution. I'm not going to say very much about pollution. It's an increasingly important area, but because of time, I'm going to just perhaps go through quite quickly. I'm very lucky because I live in, I was going to say the most beautiful city in the world. I suppose I should put Madrid first. All right, the second most beautiful city in the world. And we have beautiful buildings, and they are made out of limestone. And we have to replace some of the original, for instance, King's College, the chapel. It has these figures. They're made out of limestone. The chapel was finished 550 years ago almost. And over time, the SO2, sulfur dioxide, carbon dioxide, they form the dilute acids with rain, and these have to be replaced. But in my lifetime, we have seen enormous improvements in pollution from the gas. How can material science help with that? Well, all of our cars nowadays have these very simple, underneath the car, we have the exhaust system where the gas is, and inside this, we have aluminium oxide, and on it are palladium and platinum. And that is a way of reducing some of the emissions, of making sure some of the partially burnt emissions are trapped and converted so that there is less pollution. How old is this technology? Only 20 years. And it was introduced without real major change. It requires a slightly different petrol. So we did actually have to change the petrol for cars. The compression ratio changes. But it was introduced without trouble. So we have the potential, again, in material science to do things, and sometimes they can be introduced without difficulty. Another area, I'll skip this because it's saying the same. I mentioned the CO2, and I mentioned the story of the three bears, and you very kindly told me, some of you, the name in Spanish of the story. Okay, so now we're all understand each other. So we have the baby bear, very cold because not enough CO2. Daddy bear, too much CO2, very hot, and the Earth in the middle. And this is what the physicists will call this effect. And I put this up again because I do want you to do two things. I want you to read Bill Bryson's book, and I want you to read Dave Mackay's book, Not Just a Lot of Hot Air. The second one you can download off the web. It's completely free. But it's just to remind us that this is the variation in temperature over thousands of years, over millions of years. We do see cycles of change. And it's very important as scientists that we don't just pick up on the emotion of what is going on. It's very important to try to believe our emotion. Our emotion drives us. Our emotion makes our lives interesting. So hang on to the emotion. But when you do the science, separate it a little bit to look at the facts. I strongly believe in global warming. For me, there's no question. But if I'm asked to prove it, I can't. And that is because particularly the role of water is not fully understood. It's being modeled a lot, but be very careful. We need to understand it to be able to do even more than we are. But it's just, again, a warning that we think we know things. We know that it's true. We can't always explain it. So what choices? I showed you this. We get rid of President Bush very quickly. And maybe Obama will take action for us. And what can we do? We have to reduce CO2 and conserve energy. And unfortunately, this is where the politics come in, because every year our politicians meet and they don't seem to make any difference, not a real difference, to what we're able to do. So there's a challenge for all of us to get involved to persuade them to do otherwise. But how can we help in material science? Again, if we go back to cars, which is the best-selling car in the United States? Best-selling car in Spain. Best-selling car? Oh, the economy is not so bad. You still have cars. I've seen them. Best-selling car. Okay, United States, there it is. And it's also very, very green. I know it's made out of plastic. That's not so good. But it is very green apart from that. Now, I say this because actually in trying to get environmentally friendly cars, we have a lot to do. But already in all of our cars, we're using part of material science, which I shared with you very briefly last week. This is like a fuel cell, but it's a conducting polymer. What we have here is the exhaust gas, and it's looking at the amount of oxygen and the amount of unspent fuel. And it's trying to minimize the amount of unspent fuel. And that is governed partly by the amount of oxygen left in the exhaust. And this is a reference amount of oxygen. So again, we've got a different partial pressure of oxygen across the ceramic. If it's a ceramic, such as a coffee cup or a glass, nothing's going to happen. But if you can make your ceramic slightly porous, then it can diffuse either positive or negative ions, depending on the type of material. And this is partially stabilized, yttrium-stabilized zirconium. So this is the ceramic that looks like this. There, and I showed you this very briefly, there you've got zirconium, and it's 2 zirconium plus 4, 1 zirconium plus 4, and 2 oxygens in this arrangement. That will not conduct. There's no way. But if we remove 2 of these and replace them with yttrium with a charge of plus 3, then we create some spaces. So here we do it. So now I've replaced 2 of the blue ones with 2 of the red plus 3s, and now in order to keep the neutrality, I've got a space through which the oxygen can diffuse. Now, these lambda devices, as they are called, are in all cars now. They're very small, and they just keep the efficiency, improve it all the time. So even, again, material science with ceramics coming to help with cars in a very simple and direct manner. And there's much more we can and should do. And that's just showing the graphical output. Light bulbs I've mentioned already, and we are already using fluorescent bulbs, which are 40 times more output for the same amount of energy going in compared to the original light bulb of Edison. But the LEDs, as I said, are really interesting because they have something 20 times the lifetime, as well as maybe in the order of 1/10 of the needs of energy to make them work. There is a problem, and the problem is where the spectrum from these light bulbs. And then only now are they really coming into commercial domestic use. Because the early ones, how many of you spent over the weekend time in a police station being questioned by your police? Just checking. You know those very white lights which they will shine on you? Maybe you don't. Good. But the point about this is that the early LEDs, because of the band gap and the energy, it is a very harsh white light. So what happens now is you have your LED and you put a phosphor behind it. So the light comes off, hits the phosphor, and that re-emits at a wavelength which is more warm and gives us a color that we like in our rooms. This is quite a white light, and we in general prefer to have a warmer, more yellowy light in our rooms. And now one can do this using a phosphor. So one of the problems was to get the right colors and to get the right wavelength from an LED to make it acceptable. And you can't do it from the physics of the LED. You really do, well, you can start to with thin film, but in general, it's using a phosphor behind them. But there's something else about diodes. You know when you sometimes go into a room and the light is flickering? Well, if you could make it flicker much, much faster, we wouldn't see it. And LEDs are just an electronic device. So you could have a signal that is doing that so fast that we don't see it. But now we can transmit data. And maybe something, this is called orthogonal frequency division multiplexing. You got that? OK. What it basically is as simple as that. What you're able to do with an LED is you can change your power supply. You don't have to change the whole of it. You can just have a constant output, and then you can modulate it a little bit. And you can start to transmit data. And a group in Edinburgh University is doing this, and it's very, very exciting. It's exciting because, for instance, if you're going into one of those big body scanners, you can't use conventional type of sending of signals because the huge magnets would prevent the signal from being transmitted. This, no problem. If you have underwater, again, you can use this very, very simply. And the one I like the most, maybe the body scanner is a good example, but the one we talk increasingly about cars communicating with each other, so that we're driving along, and the car coming towards you can then speak to your car and say, I'm coming, get out of my way. And you will have seen Google in the States have developed some cars which can effectively drive themselves. And they're being trialed in a number of different states. And if you're completely blind, this maybe offers something for the future. Sounding very scary, my guess is within 20 years, these will be on our roads and safer than the car I drive. Maybe not you, but safer than the car I drive. So why I'm mentioning it? Because in fact, then if a car wants to talk to another car, you can have the LED headlights talking to each other. So again, by modulating the signal, you can start to get information and very rapid data speeds. And so you can have it for the oil and gas industry, where you could get sparks. I mentioned underwater, and I mentioned crash avoidance in cars. And so this is a really growing technology and may be very useful. And in energy, what we're now trying to do is we're trying to increase the efficiency from around 15 to 20% of the conventional solar cells, if we now go to solar cells, up to maybe approaching 60%. And again, I mentioned some of this last week. But why this is happening is, again, going away from the very conventional single crystal silicon into quite different materials, the cadmium tellurides and so on. And I'll skip this because I think you all know this and because of time, but I'll just say very briefly, in our jet engines, we have these turbine blades here. They have to be very creep resistant. So we're operating them right near their limits. And again, I put this in because if we can improve the materials in turbines, we can also improve the materials that we're using in our conventional power stations, maybe have the steam at a higher temperature than 550 than we have at the moment. How can we improve them? Well, conventional cast turbine materials look like this. You can see the grains. You can have directional cast where the grains are going up and down. And the modern turbines, this is one single crystal. So all the lattice is identical from just about here all the way to the top. And the creep properties are fantastic. I put it in because that's a history story, but we can coat them and we can have better cooling in them. But where we have seen the changes is, this is, where was the jet engine invented? Where? Cambridge, of course. Oh, well, just thought I'd mention. In the 1930s, Frank Whittle was there. A lot of the development has taken place all over the world, of course. But Frank Whittle used steel. Now we're in the nickel superalloys, and by changing to the single crystals and the air cooling and the thermal barriers, we have doubled the temperature at which the gas can go into the engine. But we've now come to the limit. And so we now have a problem. And again, this is a challenge for material science. And maybe we're going to have to go to intermetallics, things like Ni3Al, nickel aluminides. And so again, a real challenge for us is to now make the next big jump. It's like a ceramic in its properties, and we have to do it. Energy sources we covered last week. For those of you not here, I apologize. But the big thing about energy is not just generating it, but also the storage. And I mentioned the fuel cells on the Boeing 767, and that's 787, and that's a real problem because we're now trying to push them more and more. Very interesting polymer science, particularly on the ones that we're going to develop for car engines. The proton exchange membrane proton exchange membrane ones, where naphthalene, which is the fluorinated hydrocarbon, is the material currently developed by DuPont. We need better materials. These fuel cells, we're trying to drive them too hard, hence the fires on the planes. We're trying to extend their lives. We need better lives out of them. And again, enormous challenge. We can't use the zirconia, the yttrium-stabilized zirconia. Those two can be used in fuel cells, but only at temperatures of 1,000 degrees. They're very successful, but not for cars. So the whole business of storage is a big area, which I covered a little bit last week, and which, again, is something very, very important. So to finish, you can see material science is exciting. And that's hopefully why you're doing material science. So can material science save the world? Well, we have all of these possibilities. Drug release, turbines, composites, lighter aircraft. I haven't talked about glass and storing nuclear waste and solar power LEDs. Lots of options. And there's more to come. There's more to come for three reasons. One, the challenge. We need more, we need it cheaper. The second one is because you guys, many of you here, you are the future. You're going to make these things happen. And the third reason, of course, is we need to conserve energy and reduce greenhouse gas. Now, there are a number of the possibilities. So I will very quickly finish in just showing very quickly. This is piezoelectric. You all know about piezoelectric devices. When a woman is pregnant, and then in order to see the baby, you use a piezoelectric quartz-type single crystal as a piezoelectric device. And this was an idea of a British inventor in 1989, but just before 9/11, he was going to put piezo devices in our shoes. So when we walked along, we could listen to our iPods, phones, whatever, and they would be charged. And then he thought, getting through airports with electricity in your shoes, probably security wouldn't be too happy about it. But a better idea anyway is to put it in the floor. Put it in the floor, for instance, on the entrance to the metro, where many people are traveling. And you can generate power again to illuminate your signs which are nearby. So very simple technology. And in France, in 3 years ago, they are starting to do this on the pavements in busy areas to power the lights. And when I was in Cala de Mayor at the weekend, quite late, it would be daytime with a number of people who are going backwards and forwards if we could do this. Another one comes from Harvard University, and this is to take these plants. If you are a fly or a bug, and you start to sit on this plant, there is only one way you're going to end up, and that is you're going to end up eaten, because you slide down into the plant, and then you get eaten. And what Harvard scientists have done is to look at the structure, and they're now making it out of nanoscale fibers and put into it a fluid. And this, again, can give you a very, very slippery surface. And the beauty of this is that unlike the cooking ware, the Teflon in cooking ware, when you scratch the Teflon, you have a scratch. But here, if you scratch it, then immediately you scratch it, more fluid will come and fill that local area, and so it cures itself, it heals itself. And so what we have here is something which is liquid and ice resistant, very stable at pressure, and you can even put it on glass, so you can now have very good self-cleaning glass. And the options are particularly in the biomedical. Blood, our blood, is a very sticky substance, as we all know if you spill someone something. And if you can coat your knives, if you can coat things for surgery with the material that is being developed in Harvard as a very thin film, it will repel the blood very easily. But you can also use it in fridges. You can maybe reduce the flow, the friction in the flow of fuel. So that's the second one. And the last one I'm going to mention briefly is the idea of big batteries. Where a river drains into the sea, we have pure water and we have salt water. Well, that's like a battery. We have ions in one, and if the ions in the salt water can move into the fresh water, that is the movement of charge. So again, we need a membrane like in the fuel cells, and then we can transfer ions from one to the other, and we effectively have a battery. Now, these are a bit bigger than the batteries that Jose Ignacio was changing in the device. These are whole rivers. Why is this interesting? Because what you can do, this is a different idea I'll skip, because if we can do this is regions where we have big rivers going into the sea, and we could give 5% of the world's energy needs if we can use the energy of the fresh water mixing with the seawater. That's a sort of dream. It's a bit crazy. Norway have succeeded. They have lit one light bulb so far. But in other words, it needs to be made much bigger, but one can do it. I'll leave the magnetocolor. This is the new fridges. I'll leave those because of time. So what I want to end with now is the following. I showed some of you this last week. This is some modeling work, and it says this is the population, and then it starts to drop around now, actually. This is the amount of consumer things we have. Here is food per person, and it's all dropping. And that's very scary. And that is if we don't make some changes. So if we skip to away from the end of the world story, this is what you can do if you start to use technology. This is what's called the IPAT equation. This is the influence, the impact on the environment, and it's related to the population. We have to do something about population. Having enough, we don't need everything that we have. Maybe we have to lower our expectation. And then technology. And when we do that, if we introduce improvements, everything becomes stable in a good way. So there's the importance. And material science plays a key role in this. It can be done, yes, because in India, and I showed you this, I think, in the first lecture, this is this region of India, and this is the United States, and this is the rest of India. The amount of money is similar in both regions of India, much less than the United States. But if you look at the reading ability, they are very much more literate. They can read compared to the rest of India. Their life expectancy is much better than the rest of India, and the child death is much lower than the rest of India. And they did it by education. They educated the women because in many societies, the women are the driving forces to make change. And they made the arrangements easier for the women. But awareness and education. So the last 2 or 3 slides, literally, we can leave these guys to talk. They talk about a lot of things. At the G8, G10, G20, they talk about poverty, they talk about lack of food, and then they finish their session for the day and they go and have a 5-course meal. Something wrong with that somewhere. We can affect them. In some countries we can vote. In some countries maybe demonstrations, even not all countries. But we need to start to be more active in saying what we think should happen, because politicians will only respond when they hear the voice of all of us. So whilst material science is really exciting and has an enormous role to changing the world in the way I've shown, the other part that's really exciting is what one person can do. That's one person, albeit now some 24 years ago, stopping in at the time China was not the place to do this. But one person, each of us, can take a stand. This was the black African salute in the Mexican Olympics and has been adopted for the symbol of power to people. In Britain, we start to educate our children at a very young age to do the same. But what I want to finish with is it's really not power for the people, energy and so on. It's really power to the people. And maybe I shouldn't say the people, maybe it's of the people. We need to get involved, not just as material scientists in doing the exciting things. We need to get involved in making the changes happen. And that is of each of us. And in that way, sustainable development, material science, and you can save the world. Thank you.
Thank you very much.
You're really welcome.
Very, very nice talk. And we have time for some questions, please.
And I'd like to apologize again for starting late, because I realized that we finished a bit late, so apologies.
You have the microphone, please. No one? No any question? You have to say the word. You know how to do it.
Enough is enough then, don't worry. It's
We have one question here.
oh, yeah.
Well,
very
well,
young.
Completely young at heart. No.
young at heart. But
Don't worry. Yes,
okay,
please.
so you have given, I think, a very good outline of all the problems and some of the things that material science can like help with to try, I don't know, if saving the world or try to make it better. So from all the things that you presented here, which one do you think is the one that could have the highest impact? So
that's
something to concentrate in.
Something to concentrate on. Okay, there's only one. You all know the answer to this. What's the one thing we should concentrate on? Sorry? Say it again? Population. No, that's very important. You're absolutely right, population. No, the one thing on it is actually what we all share. It is the awareness and the education. Now, that's being unfair, But I say it because if we think about smoking in Europe, in the States, we knew for many, many tens of years it was not good. And only when enough people said to governments, enough, did the governments have the courage to make the changes. Now I come back to your question more fairly. So, I'm quite serious on that last part. I think it is us talking about it, sharing it, and trying to change, raise awareness, and trying to change people's views. Because then I think there really is a big, big future. But in terms of the technology, I think probably the biggest one is actually water to me, population and water. Material science can already help with population, medical science with drugs. We can use various forms of birth control with polymers, so maybe we can help a little bit with population, but maybe that's the wrong end of the body. Maybe we need to focus more on this end. But water to me is an increasing issue. I mentioned last week that I think it was in the south of Spain, even in Barcelona, you had water shortages maybe 4 years ago. And that was just a shortage. But where you have poor water, we have enormous numbers of deaths in parts of the world. We have the technology, we need to continue to refine it to make it better. And then I think we really can make a big, big difference. But of course, they're all important in different ways. So water for me.
Thank you.
What about for the rest of you? Anything that you particularly would like to see change? So what are your dreams? Really important. You've got to have dreams, and you've got to really think about what you would like to change. Because all of these things are, so many other people have put in thought and energy and time and passion. And it's really important that we each take something and we try to make a change. Yeah?
And do you really think that sustainability is possible? Because the economy always have more impact in...
Yeah. Is sustainability possible? We often people say things like, the world will not survive. Well, first of all, the world will survive. We may not survive, but the world will survive. I think actually, yes, it is possible. I think we have to have completely different ways, perhaps, of economic and social changes are needed. Here in Spain, you have, I'm sorry to have to say this, the enormous amount of unemployment, particularly for young people. And that worries me. It worries me because you here are having a good education. Is it good? Just checking. A good education. And so maybe that already it makes it easier later, difficult, but maybe easier to get jobs. But for people without this opportunity, I get really concerned. So the question about sustainability is not the material science. That can help. It can make things more available. The whole of Africa, many banking systems in Africa are based on mobile phones. That comes out of technology. But it's the attitude.